So what is today's agenda? Firstly, I will make short introduction of isystem tools. Then I will concentrate on ADIO add-on module. I will explain what are the ADIO features and capabilities. Next, I will present some use cases like power measurement, pulse width modulation, and SPI trace. In the end, I will present the means for automation. Let's start. isystem tools are built around the IC5700 BlueBox on-chip tool. The specialty is the extendability of debugger with several add-on modules. First, on top left is an ADIO add-on module. ADIO module is used for analyzing analog and digital I/O signals and driving the outputs with the signals. Next on the picture is CAN-LIN add-on module, used for network analyzing. We can analyze CAN-LIN buses and inject messages to the buses. ADIO probe is special debug and trace connector for high bandwidth tracing and profiling of controllers such as Infineon Aurix and ARM Cortex via HSSTP and so on. If more than one add-on module should be connected, the FNet hub expands the FNet ports from 1 to 4 pieces. At the back of the FNet hub is a special Ethernet port used for enabling synchronous debug and trace with two isystem debuggers on two CPUs on different ECUs. The external devices are connecting to the IC5700 BlueBox over the FNet connectors. FNet is an isystem proprietary bus system and communication protocol that provide fast communication between devices connected to the same network and enables fast communication between CPU and BlueBox, network analysis, synchronous debug and trace of multiple CPUs. On the left is a screenshot of the winIDEA IDE. It has some advanced features to speed up debugging. The real power of winIDEA can be found in its analyzer, a program and data trace visualization tool of a trace, code coverage, and profiling measurement. It also supports real-time operating system awareness. isystem can offer some advanced tool for timing analysis to cover arbitrary timing scenarios like AUTOSAR event chains. Trace Analyzer can trace and profile signals on iOS, SPI, and CAN-LIN messages with the use of the add-on modules. Here on the slide, you can see a picture of IC5700 BlueBox that is connected to the ADIO module. The IC5700 BlueBox on-chip analyzer is connected to the target with a debug and optional with trace cable. The IOM6 ADIO module is simply attached to the free FNet port on IC5700 BlueBox. The winIDEA IDE stores the configuration of the complete setup. The ADIO add-on module is part of IOM6 production line and extends the functionality of the IC5700 BlueBox. The ADIO contains 4 banks of configurable 8-bit digital I/O channels. The input-output operating voltage range is configurable. Altogether are 32 digital I/O channels. Each of 4 banks can be configured as input or as output. The sampling rate is up to 100 MHz. Additionally, the ADIO has 2 analog 12-bit outputs and inputs. The voltage range for analog pins is from -5 to +5 volts. The input sampling rate is up to 12 MHz. ADIO has special 10-pin power sense connector used for power measurement with optional isystem power probe. The isystem setup can capture and display analog and digital signals in parallel to the program code execution domain. A user can, with the use of isystem tools, measure and visualize delays across the embedded software and external signal world. Next, you can, with the use of isystem power probe, measure power consumption of a target ECU. If the SPI is connected to the digital inputs of the ADIO, the SPI communication could be recorded and analyzed. With the ADIO add-on module, you can output digital analog signals to control the target hardware. By using winIDEA fnet counter and trigger feature, is it possible to generate trigger signals for measurement equipment such as an oscilloscope or to control the target hardware. The winIDEA counter feature can be used for generation of periodical output signals. The isystem tool can be used for testing and can be fully automated by the using Python API. isystem.fnet communication network consists of devices that are connected to the fnet nodes with the isystem.fnet cables. You can add up to 4 external fnet devices, such as ADIO, to the system around the IC5700 BlueBox. The configuration in winIDEA is flexible, and you can reuse stored configuration of fnet devices or create new one. The default name for the ADIO configuration is ADIO, but you can use naming of the configured devices across the system as it suits to the best for your use case. The system recognizes currently connected fnet devices after pressing refresh button. After configuration is prepared, the Y represents recognized devices with matched stored configuration. At the bottom of the configuration window, you can see the populated available networks. There are 2 matched configurations on this slide for the CAN LIN and ADIO module, with the populated networks for the CAN, LIN, digital I/O, and SPI networks. Also on the list are triggers TC and counter 1. The fnet counters are 4 independent 32-bit counters that support the fnet operation. They use for the counting time or events. The fnet counters can generate fnet triggers and can be observed in profiler timeline. Here you can see an example of digital I/O port configuration. The name of digital I/O network, I/O signal names could be changed. You can configure the digital I/O bank of 8-bit pin direction to operate as input or as output. You have a possibility to select the voltage range of the digital I/O bank from 1.8 volts to up to 5 volts. Also, the initial state of outputs can be set. Every port display can be disabled or enabled. Likewise, the analog inputs and outputs could be configured. You can change the names of analog input and output networks. Names of analog signals can be changed. Also, the initial state of the outputs can be set. The analog inputs could be multiplied if the inputs are divided. Every pin can have display enabled or disabled. Also, a power measurement with a power probe can be configured. In that case, both analog inputs are used only for the power measurement. After the changes are stored and downloaded is performed, you will be able to access and use configured ADIO features. With the next slide, the power measurement feature will be presented. isystem provides power probe featuring a shunt resistor and different connection possibilities for connecting an ECU. With this, it's quick and easy measuring power consumption on an ECU. The isystem power probe is provided together with a ribbon cable that connects the power probe signals together with the ADIO power sense connector. A customer needs only to supply electrical cable providing the electricity from the electrical source. The image on the left explains how the power consumption can be measured with two analog inputs in respect to the ADIO. When measuring power, it is necessary that both the voltage and current are measured in the same time. A shunt is a low-value resistor connected in series to the load. The current through the shunt is measured by measuring the voltage drop on the shunt resistor, and the power is then calculated with the presented formula. The ribbon connector connects all the signals from the power probe directly all together to the ADIO power sense connector, so no need for additional wire connection for the measuring power are needed. Several shunt resistor values are supported according to the current value. The maximum current could be up to 2.5 amperes. Also, the input voltage range is selectable up to maximum 20 volts. The winIDEA later displays a current power value in the Hill monitor. winIDEA Hill monitor enables you to measure and drive ADIO analog and digital I/O pins. You can click with the mouse on the selected output voltage and select a new value. As it has been presented with power measurement slides, the Hill monitor also displays the current power measurement value. It's possible to read and modify ADIO pins with the use of isystem Connect and isystem.fnet API as well. On the right, it is displayed a short Python script. The isystem Connect API is used to write and to read digital and analog I/O pin output pins on the ADIO. With the script, we can automate the ADIO operation. Using winIDEA watch window is another option to display the values of the ADIO pins. The watch window can be configured for real-time access. Also, the ADIO output pins can be modified with the use of the watch window. For profiling of target signals, you need to configure the analyzer by adding network area in profiler settings. You can select among the available ADIO networks that are configured and enabled for profiling recording. You need to prepare FNet and network configuration for needed ADIO signals before you can configure the analyzer for recording network messages. ADIO networks will become available for selection once the configuration is complete and applied by performing a download. Also, additional program, data, and OS objects could be selected for profiling together with the ADIO network objects. After the analyzer recording is finished, we can analyze the profiler timeline with the network objects. There are ADIO signal capture along with the data and program recordings, if enabled. Later, we can use isystem inspectors in order to perform different analyses, for instance, propagation delays and event chain analysis. Triggers are an FNet module that is used to transport information of observed events on the FNet networks beside other sources of events. The IC5000 Blue Box can react to observed events by creating an action. For instance, an event on the ADIO input can trigger generation of the signal on the output. Number of generated trigger events can be monitored in Hill Monitor. As well, recorded triggers and actions can be observed in Profiler timeline. winIDEA provides up to 10 trigger channels. 3 of them are predefined. Trace trigger is used to signal the trigger in the trace analyzer. Run sync and stop sync triggers are used when two IC5700 blue boxes are configured for synchronized debugging. Other 7 triggers from TC4 to TC10 are available for the user. In this example, change of two ADIO inputs is used to trigger a generation of a signal on the output. This slide describes the use of FNet counters and triggers for generating two different pulse width modulation signals. The basic principle is that one of the counters counts the whole period when at the end it generates the trigger signal. The first counter immediately restarts counting. Another counter counts the shorter period up to where the switch from the on to off or from off to on period of pulse width modulation occurs. The other counter remains stopped until the trigger from the first counter restarts its counting. Additionally, both triggers are used to drive signal on selected output ADIO digital pin. Since there are 4 FNet counters available, you can generate 2 independent pulse width modulation signals. On this slide, you can see profiler timeline of generated pulse width modulation signals together with embedded code. Also, another digital signals and trigger events are presented. With the use of isystem.fnet API, you can automate operation and configuration of counters, triggers, and operation of an ADIO module. The Serial Peripheral Interface, SPI or SPI, is a synchronous serial communication interface specification used for the short-distance communication, primarily in embedded systems. There are 4 SPI interface signals: master input slave output, master output slave input, serial clock, and chip select or slave select signal. Information is transferred between master and slave on defined clock. Active state on chip select, low or high is selectable. An additional SPI protocol analyzer is available for easy monitoring of 2 SPI interfaces within the embedded system, either alone or in conjunction with the program execution. SPI protocol analyzer modules SPI1 and SPI2 are by default disabled because they consume digital I/O banks. If SPI1 is enabled, it consumes digital I/O bank 0, and if SPI2 is enabled, it consumes digital I/O bank 2. The SPI protocol format is described by the isystem description and SPI message description file. A SPI communication protocol and message description files are XML files, which must comply to XML schema. iSystem provides templates and documentation for these description files. You need to add an ADIO SPI configuration window, a SPI protocol, and message description file. This slide shows the SPI bus profiler timeline of a microchip digital to analog converter MCP4921. Since the control and data bits are described by the SPI protocol and message format description file, the isystem profiler can display values of the control and data bits in time. The value of data bits is displayed in float format. isystem.fnet API provides access to winIDEA functions which control the FNet devices. This API is currently supported for C++ and Python. With the isystem.fnet API, you can automate generation of signals on ADIO output pins, readout of signals on ADIO pins. You can automate configuration and operation of SPI analysis and power measurement, as well as configuration and operation of FNet counters and triggers. On iSystem web page is extensive documentation of iSystem Connect and isystem.fnet API. You can find documentation of classes and controllers. There are also numerous example scripts. Links are provided on this slide. At the end, I would like to mention that you can find on iSystem web page www.isystem.com additional help, documentation, and training on how to prepare test idea testing, on debugging with winIDEA, and on how to start tracing with the isystem tools. Now I will finish my presentation. I will give back the word to the moderator.
Thank you, Aleš, for this overview of our ADIO modules. There were some questions. One was about power measurement. You showed this additional module, and the question was, is analog input, so the analog input 0 and 1, is this needed for power measurement, or is it also possible to measure the power of a target of an ECU via the power sense port?
Yeah, you can connect if you have on your target a shunt, or then you can measure the voltage drop with one analog input, and the other is connected to the voltage inputs. So basically, you can measure two analog voltages if you don't want to use, or you can't use power probe. But since our iSystem power probe is actually very easy to configure, you have the input slots, the input connectors, and then you just connect the complete cable into the ADIO, so it's really convenient. So I recommend to use this, but nonetheless, you can measure analog inputs, while analog input 0 and analog input 1. If you measure also the voltage drop on your shunt resistor, and then you need to calculate the power consumption out of it. So this could be possible if you prepare the inspectors with the profiling, and then you can configure this inspector that will calculate in time the power consumption. But you can't use the Hill monitor for power consumption management. There will be no help there. Yeah, in that case.
Mm-hmm.
Or there's another possibility. If you directly connect to power sense the signals, like voltage drop on the shunt resistor directly and analog input from the voltage and grounding, then I think you can do and this control connector to the, then I think it's possible also to measure power, but I need to check what is this control pin. So maybe it's the best way that you send me that we send you a confirmation email that this is possible. I need to analyze what is this control signal. Yeah.
Good point. So we can answer this after the webinar in more details. another question, is it possible to connect more than one ADIO module, I mean, to this, to the 5700 platform?
Of course, if you have IC5000 with this additional FNet hub, then you just need to order the IC5000 with this hub. Then you have possibility to connect up to 4 ADIO modules together, and you can configure all 4 and use all 4 with complete feature that were presented.
Question about I2C. If it's not supported so far, is it possible to mimic it? For example, using our API and the ADIO module.
Yeah, it won't be the easy task to mimic,
Yes.
to say frankly, currently, yeah. But it's much better that you wait for our future release, and yeah. But
So,
in theory, it depends of the clocking speeds and so on. It depends on the flexibility that you need for driving the I2C bus.
Another question was about SPI. Could you please elaborate SPI hardware connection and analysis?
Yeah, so I can show. You see, this is a configuration window, and here you need to connect from a certain digital I/O bank. From the pin 0 it's clock, then you have master input, slave output, etc. Those signals, those 8 pins, basically you need to connect to your SPI bus, and then the bank is configured for monitoring. If you configure and if you prepare the description of signals and the messages and link this description file to this bank, and then you can configure what is the chip select and sampling phase, etc. So it's flexible, and then you can start tracing, start measuring with the SPI. I hope that I responded. That is what you needed.
Yeah, in addition, you can get in contact each other. And, okay, no other questions for today. The next webinar will be in May 7. It's about tracing and introductions, also based on our tutorial that is quite new. You can find on our website, and the registration is already open. Thank you very much again for attending and listening. Thank you, Alesh, and hope to see you soon again here next time. Thank you so much.
Thank you very much for listening, and stay well.